today. It's like a look into the crystal ball, as you may say, because we will talk about, we will hear about the new ideas in the energy storage TCP. There are 3 different presentations regarding different topics. There is the economics, the medium duration storage, and the building mass utilization. Presenters will be Christoph Rathgeber, Georgina Morris, Jonathan Radcliffe, and Christoph Rohringer. Yeah, and with this, I would like to start with the economics. Christoph, you can share your screen. The stage is yours.
Thanks for the introduction. Welcome everyone from my side. So as Stephanie introduced, the first presentation will be about economics of energy storage, and I will introduce to you our new ES TCP task called ECO-ENESTO, an abbreviation for economics of energy storage. I'd like to start with some basic questions. So first, what do we expect usually from energy storage? Well, on a technical basis, energy storage should provide power and capacity, and that can be electrical and thermal and whatever. By this, energy storage enables to decouple energy supply and demand, and that both in time and space. So then there is quite a diversity of benefits that energy storage systems can provide. First, there's flexibility in terms of grid services, integration of renewables. Then, which is a very important topic nowadays, reliability, security, meaning resilience of energy systems. For example, uninterruptible power supply. Then there's several mobile applications where energy storage is installed in electric vehicles, mobile phones, and so ever. And autarky is another field of benefits, thinking of island solutions and self-sufficient energy systems. So, as an example, I would like to show you this application. It's a cold storage that can be considered as a dispatchable load in the electricity grid, as it transforms electric power to cold. So assuming the situation in Germany, and let's say that a number of 20 million fridges would be equipped with such a cold storage. In this case, in our project, it was a PCM, a phase change material cold storage that has a storage capacity, or let's say for 7 to 8 hours, and needs a charging time of 2 to 3 hours. And summing this up, you can assume an overall electric power and storage capacity as indicated here. So quite huge numbers for such a system. On the bottom right, you see some pictures of the pilot installation in our lab. Now, why do I show you this example? Technically, I think it's clear, but also looking at today's topic, the relevant questions now are what is the value of such a dispatchable load first? And then second, who would pay for such a dispatchable load for such a storage? Now you can imagine of different situations, countries with a, let's say, reliable grid, probably it's not the owner and not the producer of the fridge who would like to pay for such a technology. Could it be the utility or the grid operator or the society as a whole? Well, on the other side, in countries with, let's say, a weak grid, where you have some level of grid failures, then it might be the consumer or the producer of the fridge who's interested and who's willing to pay for that. But again, it could also be the utility, the grid operator. So it's a complex situation. And for such a system, we could summarize, even if it is a good thing, it is not certain that anyone will pay for it. So that's what we will call later on a difficult case without a present business case. And that leads to the question, what are you willing to pay for energy storage? To approach this question, let's look at some existing examples of energy storage systems. You may think of mobile phones. There you pay for energy storage to have no free time at all. So acceptable costs here with respect to storage capacity are in the range of 10,000 euros per kilowatt hour. Then, also very important, to fill up the hot water, the bathtub, you need a hot water tank. And well, this is very important, but it has to be also very cheap. Here you are in the range of €1 per kilowatt hours. Another class of example would be e-mobility applications. There you might have storage capacity costs of around 500 euros per kilowatt hour. Some more examples, looking at industry. Here's an example of improving the energy efficiency of industrial processes. So acceptable costs are in the range of 100 euros per kilowatt hour. Then there are grid services. Here you can assume costs of 250 euros per kilowatt hour. And at the end, also very popular is the integration of renewables by increasing self-consumption. So for such home PV batteries, we can assume costs of around 1,000 euro per kilowatt hour. So many examples of nowadays costs that are more or less accepted by the market and by end users. So with this, I'd like to come to the goal of the new task Ecoenesto. So the overarching goal is to contribute to a better understanding of first, how a certain value is created from a certain benefit of an energy storage technology or system, and then how this value can be translated into a business case in a systematic way. So as illustrated here, it's these two steps that interest us. It's going from a benefit, I showed you some examples, to the value. So with value, we mean the question, how much would somebody pay for different benefits? And then step two, from value to business case, who pays for the benefits? The scope of the task are in principle all energy storage technologies, electrical, thermal, chemical, and all relevant energy storage applications in the system, both centralized and decentralized, and also all demand sectors, electricity, heating, cooling, as well as mobility. We have a few objectives we would like to work on. First, a collection of methods, of existing methods to evaluate the economics of energy storage. Second, also deriving from these existing methods to have KPIs, key performance indicators, to evaluate energy storage economics. Then we would like to work on an inventory of economically interesting energy storage configurations, and also an inventory of what I called before difficult cases, where you don't have a business case right now. Another objective is to compare energy storage configurations to solutions with other flexibility measures, for example, demand side management, and also to solutions without energy storage. And also a very important point, which will, of course, be different in the countries we are looking at, is to analyze the regulatory framework conditions and their influence on energy storage economics. One example for such an economic evaluation approach is what we call the maximum acceptable storage cost. So this method has been developed in a preceding task. Here we focus on the costs per storage capacity installed. That means euros per kilowatt hour. And these costs are calculated on the basis of, let's say, the economic environment of different user types. And this can be characterized by the expected payback rate, the interest rate, and the reference energy costs, the costs of the energy to be substituted. So as an example, looking at the picture here, you see a solar thermal collector installation on roof of buildings group. So it's a solar thermal storage for local district system. That means we are on the building sector, where you can assume payback times between 15 and 20 years and an interest rate of 3 to 6%. And well, as we developed the method, we assumed reference energy costs in the range from 60 to 100 euro per megawatt hour. And using this input data, we calculated the maximum acceptable storage costs on the y-axis as a function of the storage cycles per year on the x-axis. And now, as I said, looking at the building sector, you see these two lines indicating the range of acceptable costs. And for the given example, for the given application, we can calculate acceptable storage costs of seasonal storage in buildings from around 1 to 2.3 euros per installed kilowatt hour. And of course, going to industrial applications, you have lower payback periods of 5 years or less, higher interest rates and lower energy costs. And as another example, again, the mobile storage for energy efficiency in industry. Here we have around 240 thermal cycles per year. And then, of course, higher storage capacity costs are acceptable. In this specific example, it's around 16 to 38 euro per kilowatt hour. So this is one method we would like to go on with, would like to extend, and also to apply it to different types of energy storage, not only thermal as in the past. Here you see some information on the task management. So the task manager will be the German Energy Storage Systems Association, VVS, in person Andreas Hauer. As task manager, the runtime of the planned task is starting in July this year, and then 3 years until summer 2025. And on the bottom indicated are the subtask leaders and the task contributors. If I missed a logo, so please excuse. It's really quite a large group already that is interested and would like to contribute to this task. With this, I'd like to thank you for your attention, and also a special thank to the project management Jülich to acquire funding for this task.
Okay, many thanks, Christoph. This was a nice overview of what's going to happen and the challenges. So let's see, is there any question? If you have, so please raise the digital hand or write into the chat. Well, if not, I take the chance and ask something. I was curious about these are now the costs which occur and the making and the runtime and so on. But what did you take into account that maybe sometimes there's also the possibility of some governmental funding, like some grant-aided money you can ask for? Sometimes it's depending on the technology you use, but is this also part of the work to also consider where this is possible?
Yes, well, if public support or public funding is a relevant part of a business case, of course, it needs to be considered. I think it's part of what I called analysis of the influence of the regulatory and the political framework. So, well, at the end, some of the success stories that we will find were that successful because of political or economic boundary conditions, not only so successful by the technology itself. So, for example, a high difference in electricity tariffs, daytime, nighttime, which can also be politically motivated. So yes, it's a relevant part, and probably will depend by the country we are looking at, but therefore we need a large group of experts from many different countries to identify what we called in our discussion some kind of common disruptors to enable business cases for energy storage.
Okay, sounds very interesting. I guess it can be a good help to push the storage forward.
Hopefully, yes.
So many thanks. If there are no further questions, I would move on to the next talk. In case there are any questions later on, just write into the chat and I will forward to Christoph. So many thanks. Then
Thank you.
I would ask Georgina and Jonathan to share the screen. Many
okay,
thanks.
can you see my screen? Okay.
Perfect, yes, thank you.
Right. Okay, thanks, Stephanie, and good afternoon to everybody. So I'm Jonathan Radcliffe. I'm a reader in Energy Systems and Innovation at the University of Birmingham. And I'll give a short presentation on a new task that's being proposed on large-scale and medium-duration energy storage. And Georgina will follow up with a few details of some of the sort of big investments that are going into this topic in the UK from the government. So I'll just click on. So yes, this is a new proposal, a new task that is being proposed by Professor Seamus Garvey, who's at the University of Nottingham. And unfortunately, he can't be with us today. He's had quite a busy week this week, doing other events on medium duration energy storage. So I'm just going to cover some of his slides, but I'll also introduce a few of my own to give a bit of the context from the UK. So the overall goal of the proposed task is to support the introduction of this specific scale of energy storage that covers what we call the medium duration that I'll define in the next slide, and how that can be applied into energy systems globally in different markets as a way of helping achieve our net zero targets affordably and quickly. So I'll give a bit of a sort of rationale and scope of the task over the next few slides. And the task would aim to start later this year in the summer. And we've had a previous task definition workshop in December last year, and we're following that up with another one to come in the next few months. And we've just got to arrange the date of that, but when that is arranged, then we'll circulate the details for that. So it's being led by Seamus, supported by myself and Georgie. So the rationale really is by looking at how the fossil fuels really have provided a lot of flexibility on our energy systems over multiple timescales. And as we transition away from the use of coal and gas and oil, then we're going to need to find ways of meeting those energy system demands from other sources. And it's clear that fossil fuels, I mean, that they provided high energy dense fuels that were convenient and affordable, but they also provided a lot of flexibility and resilience over timescales from those seconds over months and years indeed. So we need to find other ways of meeting that flexibility challenge, and there are a number of ways that can be done, whether it's through some demand-side response, greater interconnection, and potentially in the future by using some carbon capture technologies alongside fossil fuels. But energy storage has got a really attractive way of meeting that demand as well. And within that, the medium duration is a critical part of the system for providing that flexibility that I'll describe. And we look at energy storage as covering various different regimes of timescale that I've listed at the bottom here, or this is from Seamus. First of all, that very short duration timescale that covers sub-second to a few minutes, where an important characteristic is the ability to ramp up quickly, so to provide power over short timescales and to meet the demand, very quick responses. And then the sort of short duration storage, once that ramping is met, to provide especially power over a range of a few minutes to several hours. And then there is this sort of period of what we call a medium duration that would cover that sort of 4 hours over a few days and maybe up to a couple of weeks. And then beyond that, multiple weeks, months, and between seasons especially. And that's captured within this graphic here that you can see, where we look at the discharge duration of energy storage along the x-axis, and then the costs of providing the storage over different durations from the different regimes. And certainly for some of the short timescale energy storage options, the cost increases very quickly as you look to increase the duration over which it's able to provide that energy. And we can consider things like flywheels or supercapacitors being able to meet that short duration storage requirement, that very short duration storage requirement. And then for the sort of longer time scale, between 5 minutes and up to 4 hours, there's the cost per power that becomes more important, and batteries are providing some very good solutions in that space. And then if we just skip to the sort of longer duration energy storage, it's more about the cost per energy stored that is important, where we have less cycling, which is maybe over a few times a year, or maybe 12 or so times a year. And so it's that cost per energy stored that's important. And we can think of maybe chemical means such as hydrogen that are suitable over those durations. But within those two limits, we have the medium duration energy storage, where we're looking for a balance between the cost per unit power provided and the cost per unit energy that can be stored. And it's that sort of area that we're looking to focus on within this task. And we can see that a number of thermomechanical technologies are perhaps best suited to meeting that demand. And that could include sort of gravitational potential energy storage, compressed air, liquid air, and some other heat pump heat pump technologies that could meet those demands. And to give a bit of context from the UK energy system, just looking out to 2050 and how scenarios are showing the supply and demand will be changing, we can see on the left-hand side that electricity demand will be perhaps doubling out to 2050 to meet our net zero targets. But on the right-hand side, we can see that this is going to be mostly provided from variable renewable sources, either wind or solar. So we're going to have a bit of a crunch when it comes to losing a lot of the flexible generation that's traditionally provided by fossil fuels, and needing to meet that through other means. And as an example here, this is a winter week that I've taken the demand from 2019, and the overall demand is in the black line here, with the different generation profiles in the colors scaled up to what we might expect in 2030, so that we can see that the residual load in the red line here that goes sometimes negative, meaning that there is a deficit, a surplus in the energy being supplied by the low carbon generation technologies, through to positive, where there's a deficit, there's a positive load that needs to be met. But this is sort of alternating across days, of the order of several hundred gigawatt hours per day. So that's the sort of scale of balancing that we're going to be looking at across those sort of daily timescales. And so that sort of sets the rationale for looking at this medium duration energy storage. And the goal and objectives are around forming a community in this area to start with, to bring people together from across the different member states to understand how people are addressing these issues, get some clarity on the definitions of how we understand the different energy storage regimes, and review what's available at the moment in terms of the technologies that can meet that now and potentially in the future. And then also understand how other ways can meet this demand over those timescales, and what some of the limitations are on the different energy storage technologies that are being proposed are in terms of the different resources that need to be available geographically, for example, or geologically. And then finally, looking at some of the policy and financial frameworks that would be needed to get the value out of these energy storage systems in the future, so that they can be commercialized and attract investment into the technology development. And our sort of initial view of how we'll structure this task is given before you there. So there's 8 subtasks that we're just revising at the moment, and we'll probably consolidate into a smaller number of subtasks for the next workshop, but really taking us through the definitions, reviewing technologies either now or in the future, modeling what the role of storage could be, understanding the different resources that are needed, and then into how we look at different financial and policy frameworks. So we're a bit short of time, so I'll just maybe just skip through this, but we've done some other work around an energy storage roadmap in the UK that really highlights the gap in this, both in terms of research and innovation that's now being filled, but also the need for more market pull mechanisms to bring those technologies forward. Okay, and I'll pass over to Georgie now to give you a bit of background on some of the support that's coming from the government recently.
Thanks, Jonathan. Yeah, so I'll just quickly run through this. I think I just wanted to provide some context around, why the UK is proposing this task, why we think it's really important, and also in starting this task, providing a mechanism to share learnings from a programme that we're running here in the UK. So it's the longer duration energy storage demonstration innovation competition. It's a funding opportunity in which we're supporting projects around TRL, so technology readiness level 3 and 4. So that's about prototype demonstration, and then a later stage technology actual demonstration. So it's for those technologies that are pre-commercial. And so in the UK, we think that's a really exciting thing to do in terms of building and proving this tech and doing that at scale, but also in sharing those learnings internationally, which is how this will feed in to the task that Jonathan has just talked about. And if I could just have the next slide, Jonathan, that would be great. Thank you. Yeah, so just an update on this. So very recently, the UK has, we've announced the projects that we're funding through phase 1 of this competition. So it's nearly £7 million of capital funding for 24 projects across the 2 streams. And these include projects in thermal, power to X and electricity energy storage. And here's just some of the examples of the sort of technology that we'll be funding. So SunAmp, which are a company from Scotland that have kind of heat batteries for households. Cheesecake Energy, which is based in Nottingham, which is around compressed air energy storage. And then a salt cavern hydrogen storage project over in Northern Ireland. And so, yeah, all of these projects will be doing some level of knowledge dissemination, but also we just want to kind of build on that internationally. And as Jonathan said, there's a real rationale and need, I think, for this medium duration, large scale energy storage technologies and how they integrate into systems. And so I just have one last slide, I think, which was, oh no, a couple more, I remember now, Jonathan. Yeah, so this feeds very much into the other task that we heard from first in this presentation today around policies and markets and economics. And so in the UK, the storage is participating in lots of different markets, local flexibilities, balancing mechanisms, so on and so forth. But as well, we think that the role for energy storage will change in a future energy system. And we're doing a consultation, and we've done a call for evidence, which is where government engages with the sector on what we think a fundamental market intervention might look like. And so in the UK, we're not only supporting the innovation, the technology with capital funding, we're also thinking about market reform and market intervention, and also around, okay, so if this is all of our learning, how do we go about sharing that internationally? And so I think one last slide was just to point you in some more directions. So if you're interested in this, I'd encourage you to get involved in our task. But also we have lots of information here about the Smart Systems and Flexibility Plan, which sets out our commitments to consider the market intervention. We have information on the projects. You can find all 24 projects online and look at who has been funding and who's achieved funding and the technologies that we're supporting. And also some other interesting links here. I definitely recommend you have a look at the energy storage roadmap, which Jonathan has worked on and is a very useful resource for us. So that's all I kind of had to add, with thanks to Jonathan for running us through what the task will look like in the future.
So many thanks for the presentation. It's a lot of information. I think you summed it up very nicely. It really shows good where a gap is and how to work on it, to fill it with information. There was a question in the chat, which I just want to share. 1 second.
Yeah, there's a question from Christoph around whether redox flow batteries should be considered. And I think, yes, yeah, it wouldn't be limited to the thermomechanical, but flow batteries, I think, fit within that. Within the scope of this task. Okay. And indeed, I think any storage technology that can meet those demands really is appropriate. And certainly as time goes on, we can see the landscape changing as to the regime in which batteries and maybe hydrogen will operate. But also as innovation increases and the technology costs come down, then things like compressed air or liquid air or gravity will maybe expand across those. So it's really understanding how the system will change.
And that's a good point from Jonathan there around the system. For me, I'm quite technology agnostic, and it's more around, okay, what service do we need in an energy system? So that service is flexibility and also things like as auxiliary services, inertia, so on and so forth. Okay, so what are the gaps and where can energy storage contribute? And then lay on top of that, which technologies can provide those different services? Because I think, yeah, it's good to have a number of different technologies that can provide a service, not just one. So I think that's an exciting way of how we're proposing to structure this. So what's the need for it? What do we have already? And then what do we have coming up in the future?
Okay, many thanks. Yes, I guess this is an important point to find also the right technology for all the different needs as well. Okay, many thanks. So as there's no further question as far as I can see, maybe if there is, you can write in the chat and I could forward. And well, so I would go directly to the last topic. Christoph, if you would like to share your screen.
Yes, let me try. Okay, should be coming up now. Let's make it large. Is it visible?
Yeah, perfect.
Okay, great, thank you. And you can hear me, obviously. Wonderful. Yeah, thank you for the introduction and also the opportunity to present at this third ES OnSeminar. I'm Christoph Rohringer from AE Intec in Austria, and today I want to present to you a new IEA ES initiative that we are currently preparing. It was very nice to hear in the previous two presentations also what's going on, and I think Christoph Rathgeber and his task, they are already well on the way. And just the previous presentation now, they had their first task definition meeting. We are, I think, a step further still. So we presented our idea at the last EXCO meeting, and now we are starting to prepare our first task definition meeting. I want to take the opportunity today to showcase our general idea, our approach, and tell you a little bit about our initiative. We want to work on standardized use of building mass as storage for renewables and grid flexibility. So what does that mean? On this first slide, I have a picture of thermal building mass activation. So basically it's heating tubes or cooling tubes, if you will, in a structural element of a building. In this case, it's concrete. And if you take the Wikipedia definition of thermal building mass activation, it basically says, okay, this is a technology to regulate temperature in a building. So you can use it for cooling or for heating. What it does not yet say is that this is actually an energy storage. So you can utilize the available building mass and the thermal inertia of these structural elements to store energy. So here we have a technology that has untapped potential as an energy storage. And on the other side, we have a challenge to face, and this was also already presented by the previous presentations, but I will go through it once more maybe. We basically have the goal to move towards a renewable-based integrated energy system in the future. And I think given the current circumstances, this has become even more urgent, unfortunately. To meet this challenge, we will need to increase the share of renewables in the energy system. This will bring about certain challenges, and we heard that already. We have almost always a mismatch between energy supply and energy demand. And also speaking about central and decentral energy generation, there will also be a shift. So we are moving away from fossil-based centralized on-demand energy generation towards decentralized renewable-based energy generation, where our consumers will transform into prosumers. So no longer only using energy, but also producing energy. This will put a significant strain on our grid infrastructures. Both thermal and electricity systems are equally affected by this. So the outcome of this challenge is we will need storage, and we will need lots of different storage. I like the presentation from before very much, where we say, okay, where are the missing pieces that we need to overcome this challenge? And we think that thermal building mass activation can be such a puzzle piece to come up with a very good solution. Where do we think that the thermal building mass activation can shine? Basically, we tried to condense it in three major points. The first one is thermal building mass activation allows us to intensify or even enable local renewable energy consumption. So basically, I can use it as a buffer storage for example, solar thermal peak supply, store that in the building mass, and be able to bridge a gap where there's no solar thermal supply, therefore increasing the local self-consumption. Also, it's worthwhile to note that thermal building mass activation is also a large area heat dissipation system, which allows us to reduce temperatures while still getting the required amount of power into the building. So this also helps to enable renewable energy integration on the building level. Moving away from the local level, thermal building mass activation also allows buildings to interact with overarching energy grids. The middle point here highlights the utilization of excess renewable electricity from the grid. So this is something we are already experiencing in Austria. So in the easternmost part of Austria, we have a lot of wind power, and there's currently a search where to put it all. And I know that Germany has similar challenges, or if you will, you can call it potentials. And this thermal building mass activation coupled with a heat pump, for example, provides a power to heat solution to really use this electricity in a meaningful way. The last point is also dealing with overarching grids, this time not electricity, but thermal grids, so heating and cooling grids, where also a building through its thermal inertia can provide flexibilities for load management in these grids, basically smoothing out the load curves and reducing peak demands, reducing the switch on times for fossil backup heating, and reducing also maintenance hours, enabling these thermal grids to further integrate renewables into their portfolio. We're actually quite happy to have also some ongoing projects on this right now, where we could successfully close basically this feedback loop. So we get data from real operating grids, predict the weather forecast, and then our algorithms provide them with a control signal for their load management in the end consumer buildings. To highlight a little bit what's also happening in Austria's industry or market, if you will, besides these, let's say more scientific approaches, I have two examples today that I want to present. In general, it's noteworthy that in Austria, over 50 plants are already in operation that rely quite heavily on thermal building mass activation. And we also have a very diverse portfolio in building sizes on the one hand, but also in building usage. So we have residential buildings, office buildings, accommodation, education, healthcare, even manufacturing or warehouses. So really a very diverse usage of this technology. Also supporting different construction methods and activated materials besides the usual suspect concrete. The first one I want to showcase is the MG22 in Vienna, which is a residential quarter. So it's not just one building. As you can see in the right-hand picture, it's a building complex. It's, excuse me, it's 160 flats with 25 kilowatt hours per square meter and year energy demand. And what they have is a very interesting energy system. So they have geothermal boreholes and heat pumps, and they are connected to wind turbines. All of these buildings are equipped with thermal building mass activation, and they use those storage capacities to basically boost their self-consumption of renewable electricity from the wind turbines, utilizing the heat pump as a power to heat application. The second project or object I wanted to present is elementary school in Halvang, also in Austria, with 2,800 square meters conditioned area and 1,000 cubic meters building mass activation. So a different usage type, and you can see also different size of building, and also noteworthy a different energy system, in this case 280 square meter solar thermal, highlighting the technical use case I was talking about earlier, where you can store the solar thermal energy in peak supply times for low supply times. And in this case, they are even storing it not only over days, but over weeks and even months to bridge these supply gaps. What's maybe also worth mentioning is that these buildings are offering also architectural design potential. In this case, the elementary school Halvang, they won even the state prize in Austria for architecture and sustainability in 2019. As we are in an earlier phase of shaping our task, we tried to think about with the connected experts about topics that affect thermal building mass activation and that would be worthwhile to discuss on an international level. In doing this, we came up with this kind of structured chaos, if you will. And we identified so far 4 major areas where we want to work on this technology. One is the integrated energy system, and this was also part of the presentations before, I think very important. Storages need to interact with the energy system and also with each other to provide us with a, with a resilient portfolio for energy storage. So we want to look at synergetic interaction with other storage technologies. We want to look at sector coupling, using different energy vectors for this thermal building mass activation. We want to see how this technology interacts not only on a building level, but also on a quarter and district level, even how it interacts with overarching grids and what digital interfaces are necessary to do so. Moving away a little bit from the systematic view, we also want to look obviously at the technology itself, and most importantly at the construction possibilities and how to operate it. So how can I build, design and operate thermal building mass activation to ensure I have high user comfort, to ensure I have active zoning, for example, in office buildings where you might have different usage areas relatively close to each other. How can I do hot water generation if everything is low temperature based? How can I bring thermal building mass activation efficiently in new construction projects, but also refurbishment? What are my possibilities in doing it horizontally or vertically through the building walls? And in conjunction with these questions, what is the potential for prefabrication for thermal building mass activation? The second batch of these main challenges is highlighted here. So on the left-hand side are the non-technical challenges. And I quite like that this was also a topic in the previous presentations. A lot of stuff makes sense on a technical level, but for it to be feasible, there needs to be a business case and there needs to be the adequate legal and regulatory frameworks. So we want to look at what's currently there, legal and regulatory regulations basically, but we also want to look at what might need to be there for thermal building mass activation and all these flexibility topics in order to work probably. So what are end user incentives? How can I motivate people to offer up their working and living areas as a flexibility storage? How can I enable them to partake in this balancing energy market? How can I integrate energy communities and deal with topics of these centralized grids like supply guarantees, for example. And lastly, and I think this is very important and also one of the main beneficiaries of doing it on an international level is standardization and KPIs. So right now, thermal building activation as a storage is not yet there where it is a standard solution, but we think this is very important to accelerate the market uptake and the market penetration. So we want to look at its core strengths, its core applications, how we can compare and grade thermal building mass activated systems to define a levelized cost of storage, perhaps. So we heard that in the first presentation of Christoph Rathgeber. So there's for sure some synergy and also levelized cost of flexibility to define these terms. Apart from the content, maybe also a brief glance at what's going on currently. So what activities are ongoing in Austria and beyond? For Austria, there's actually quite a lot of interest from our government as well. So our ministry just recently launched an R&D study on thermal building mass projects in Austria, which we're also very happy to lead. There's also additionally to that a national subsidy program that launched last year for the planning and implementation of thermal building mass as a storage. In parallel to these central activities, there's also a large portfolio of national research projects on flexible energy communities and storage applications. From what we've received as an echo so far, there is activities ongoing in Germany. So I had a lot of good talks with partners from there already, in the Netherlands and in Switzerland, and I'm very sure that there is a lot more going on that I'm not yet aware of. And I'm looking very much forward if people also from this webinar might want to share what's going on in their local market areas. As a last slide, maybe some advertisement and also a status quo. So where are we right now with our activities? As I said, we are just now starting, so we are currently preparing a first task definition meeting. For this, we chose an online format. It's unfortunately a sign of the time, but yeah, maybe we can also reach out to people who would not be able to attend personally. This event will take place on the 27th of April from 10 to 15 Central European Summertime, including some breaks, of course. And yeah, in case of interest, please just contact me. I would be very happy to forward you the invitation and provide some additional information if need be. And I think I saw in the chat that these presentations will be shared anyway, but I will also post my email in the chat. So yeah, you can easily contact me. That's it from my side so far. I hope that yeah, we will generate some echo from the community and find interested people who want to participate in our activity. Thank you very much.
Many thanks, Christoph. This is a quite nice overview in yeah, what is the early stage of a task and what's going on, and so many questions. What to consider, I can imagine. It's quite interesting. We have 3 questions in the chat. I would like to read it. So the first one was, sorry, the first one was from Leonardo Nippi. It was, how do you define the levelized cost of flexibility?
Mm-hmm. It's an excellent question. It's a difficult question, but an excellent question. This is actually something I have not yet defined. So this would be a work item for the task. We know that in other IEA activities, there has been work on defining this term of flexibility and also maybe coming up with a levelized cost of flexibility very much on a system level. And we want to do that for the technology level as well. So yeah, I cannot give a definite answer yet, but if you're interested in working on these questions, you are, of course, very welcome to join at least the task definition meeting also.
Okay, many thanks. Yeah, also written, so I hope this is answered so far. And another question is from Basar Kagla. Excuse me if the name is pronounced super wrong. The question is, will there be a study on the regulation of response time of the system to prevent time delay between supply and demand?
Mm-hmm. Also a very good question. I think this is very central. So I had a term on the slides that I didn't specifically mention, which is model predictive control. And I think it goes a little bit in this direction. So from the work we've been doing on the technology, we see that there is the inertia that we want, but there is also the inertia that we don't want, which is the reaction time. And for sure, this needs to be a central item in the task on a technology level. And of course, also on a system level, yeah, to provide the grid operator with some information how fast we can buffer up yeah, energy peaks, basically. I hope this answers the question.
Okay, thank you so far. Sorry. Okay, there's one more question from GW. Is TBMA also a measure applicable to existing buildings? If so, do you have examples?
Yeah, super interesting question. Yes, it is, and we have 2 big research projects going on this topic and 1 finished one. So we also see potential for thermal building mass activation in refurbishment, which is especially nice because basically the storage is already built. What we need is a way of accessing it. And what we've been doing in this chain of projects is basically using prefabricated facade elements, which in one step not only improve the thermal insulation of the building wall, of the existing building, but they also include an active layer, bringing that into contact with the original building material and using that for the activation of the masses. And this has been quite successful. There's actually also a fairly large demonstrator in Graz. It's currently being built with exactly that technology.
Many thanks. I guess this is answering it quite well. Then there is a comment, just a recommendation would be to have a look at ongoing activities in the IEA EBC TCP regarding this topic. I guess you may be aware of. If not, there's the link in the chat for, so if you're interested in. And another comment from Jonathan, just gave the presentation before. I'm not sure of the value of the levelized costing in general. The usefulness of LCOS is maybe something for Eco and Nestor, so the talk Christoph Rathgeber gave before. I guess there's an overlap as far as you can see between the two talks between you, Christoph, and the other Christoph, not only in the name, but also
make the confusion perfect.
Exactly.
Yeah.
But it's clear that there are many things connecting with this topic. I think it's quite interesting. So my personal opinion is that also the building was quite interesting to consider as a storage. Yes. Okay. So.
Thank you so much. I will stop sharing.
Yeah. Thanks.
Or have I already?
No, it's still there.
Okay, I can pause it. How can I? There we are. Okay.
Okay, perfect. So many thanks to all the speakers. It was really a nice overview, a lot of information in short time. But well, I think it's quite a nice view in the future, if you may say so. What are the upcoming topics? And I'm really curious about the first results. So with this, I just want to share the screen again for the next energy storage online seminar, which will be on the 14th of April at 2 o'clock in the afternoon. The next topic will be the geothermal energy and competing uses in underground space. The two speakers are Burkhard Sanner, which is an expert in geothermal energy with a long time experience, and Sebastian Bauer, who is at the University Kiel, who is working on the topic competing uses in underground space. And I'm really looking forward what this topic will bring, and also what how it is possible to connect also to the energy storage in general. So what we can learn about this. Well, then many thanks so far. Many thanks to the speakers and to the audience and the good discussion. And yes, I hope you have a nice afternoon, and or wherever you're living, a nice day, and see you next time. Goodbye.